A dust storm on Mars could not knock you over. This is the thing films get most wrong, and the correction is simple arithmetic. The air pressure at the surface of Mars is about 6 millibars. Ours is 1,000. So the atmosphere there is well under 1% as dense as the air in the room you are in. The push a wind gives you depends on the density of what is moving as well as its speed. A Martian wind at 100 kilometers an hour carries roughly the force of a gentle breeze here, about the pressure you feel from a fan across a room. It would not knock over a person, or a lamp, or an empty box. What it does do is lift dust, because the grains are so fine and the gravity so weak. Once lifted, dust stays up for weeks. Every few Martian years, a storm grows until it covers the entire planet, and the surface is hidden from orbit for months. Sunlight at the ground drops to a fraction of normal, and solar-powered machines have been lost to that darkness. So the danger is real, and it is not force. It is dust in the air, dust on the panels, dust in every hinge and seal, and dust that does not settle for a very long time. A quarter of the air freezes onto the poles every winter. The Martian atmosphere is almost entirely carbon dioxide, and at the winter pole, it gets cold enough for carbon dioxide to freeze straight out of the air onto the ground, about minus 125 degrees. So each winter, a cap of dry ice a meter or two thick builds up over the pole. The gas that forms it comes out of the atmosphere everywhere on the planet, and the air pressure across the whole of Mars falls measurably as it does. Then that pole tilts back towards the sun, the ice turns straight back into gas without melting, and the pressure rises again. The swing is around a quarter of the total atmosphere, moving from air to ground and back, twice a year. Nothing like this happens here. Our seasons move water around. Mars moves its own sky. We know it because two landers in the 1970s carried simple barometers and sat in place for years, recording the pressure day after day. The graph is a clean seasonal wave, and it has been confirmed by every lander since, most recently by an instrument sensitive enough to feel the pressure change from a passing dust devil. Sound travels at two different speeds on Mars. Until recently, nobody had heard Mars. Several missions carried microphones, and none returned usable sound. In 2021, a rover landed with two, and they worked. The recordings are quiet. Wind, the whir of the machine's own arm, the tapping of a laser on rock. Sound is faint there because the air is thin, and it does not travel far. Then the analysis turned up something nobody had planned for. In carbon dioxide at that low pressure, high-pitched sound travels faster than low-pitched sound. The measured difference is about 10 meters per second, in a medium where sound moves at around 240 in total, compared with 340 here. The practical effect is strange to imagine. If two people stood a distance apart and one spoke, the high parts of the voice would arrive slightly before the low parts. Over 100 meters the gap would be noticeable. A conversation across open ground would not simply be faint. It would arrive out of order. Nowhere on Earth does this happen at any pressure people live in. It was predicted from theory beforehand, and then measured, which is the best way for anything on a list like this to arrive.